Therefore, it's 9:30, and we are starting the meeting. Good day, everyone. Today is 7th of September, and we are starting the 4th edition of Zeldovich meeting. The previous 3 meetings were held in Minsk, in Belarus, in 2008, 14, and 18. And this year, unfortunately, due to pandemic, like many other organizers, we had to go online. Therefore, this is virtual meeting. It is organized by ICRANet Pescara, ICRANet Minsk, ICRANet Yerevan, centers of ICRANet in Italy, Belarus, Armenia, and other countries. And this particular meeting also co-organized by the National Academy of Sciences of Belarus, and there is a host in Belarus in the Institute of Physics, which is connected to the meeting. Traditionally, the meeting, of course, is devoted to the memory of Yakov Borisovich Zeldovich, famous Russian physicist and chemist who made very important contributions to both fields, physics and chemistry. Also contributed to the defense of the Soviet Union at that time. And he is known as founder of the Russian School of Relativistic Astrophysics. And traditionally, every meeting, we have many participants who were close collaborators of Zeldovich. In particularly, in this meeting, we have at least 8 persons who worked with him directly. They are Rashid Sunyaev, Dmitry Sokolov, Alexei Starobinsky, Alexander Dolgov, Maxim Khlopov, Nikolai Shakura, Jan Einasto, and Valery Chichotkin. Of course, we have many other collaborators from internationally who are connected to the meeting and will give their contributions. Therefore, let's start. We have every day 3 sessions. The first session is devoted to gravity this morning, and Professor Ruffini, who is director of ICRANet, will speak first today. So I'm Professor Ruffini, can you speak?
Hello, yes.
Ready? Yes.
We are getting ready. Just a moment.
Just a moment.
Can you speak? Hello, can I see you?
Yes, we can hear you, but cannot see you in a moment.
Viewpoint.
Yes, I can see you.
Yes.
Okay, you are presenter now. Can you share your screen, please? Good, we can see it.
Okay.
Okay, please.
Good morning, everyone, and welcome to the 4th Zeldovich meeting. I will speak about the discovery of the moment of formation of a black hole in GRB 1901-14c. But I start first with some historical picture. Everything started in microphysics from the Planck constant and the length associated to the Planck constant, to the Compton wavelength and the Broglie wavelength. And similarly, gravity on a classical level has been characterized by another length, not by h bar, but by g, and related to the mass of a gravitating object by what is the characteristic length gm divided by c squared. These two lengths characterize microphysics and macrophysics, but it's only when they merge together that the characteristic mass come in is the Planck mass, at which the gmc squared and h over mc do coincide. I have been developing the role of this Planck mass in the book Einstein, Fermi, Heisenberg, and the Birth of Relativistic Astrophysics, which is finally being completed. And there I present some of the work, fundamental of Albert Einstein, of course, and I will mention one. And there also the role of the work of Fermi, the Thomas Fermi atom, that Thomas Fermi that Eugene Wigner in his Hungarian accent used to say, it works much better than it should. And then, of course, also the work of Heisenberg and Euler on the vacuum polarization, which we are almost for the first time in astrophysics verifying and observing. I will refer in this presentation not to all aspects of relativistic astrophysics, but focus on gravitational collapse. And there are two papers which were presented by Einstein on the stationary system of self-gravitating particle, a beautiful article in which Einstein just introduced study a cluster of self-gravitating particles, and from this cluster also discover many years before we were realizing the role of the unstable circular orbit at 3M. And a few days, this was May 10, 1939, this superb paper, which is still today attracting a lot of attention. And on the other side, on July 10, 1939, Robert Oppenheimer, at the time still in Berkeley, presented the continued gravitational contraction paper, the classic paper in which the approach to the Schwarzschild radius was considered, that the radius of the star approach asymptotically its gravitational radius. Light from the surface of the star is progressively reddened and escape a progressively narrow range of angles. This is the approach to a Schwarzschild solution, the way we have been used to think, and we are still developing. The era of relativistic astrophysics started practically with three papers. One by Riccardo Giacconi, Herb Gursky, and Frank Paolini and Bruno Rossi, the evidence for an X-ray source outside the solar system. This beautiful paper of 1962 introduced the SGO-X1, still today a mysterious object that we are trying to understand through the physics of gamma-ray burst, which I will speak in a moment. The other paper, just a few months apart, was the paper of Martin Schmidt of the discovery of the quasar 3C2733 with his famous jet. And there again, we are progressing even in this hour in the understanding of this jet structure. And of course, the most strong result was the discovery of the Crab Nebula pulsar, and by Hewish and Jocelyn Bell in 1968. And here you see at a millisecond apart the image of the Crab pulsar and the companion star. Well, this really made a fantastic impact, and things have drastically changed, and this really signed in the field of gravitational collapse the starting point of relativistic astrophysics, these three papers. I was in Princeton in the group of John Archibald Wheeler. We just turned to the analysis of an even more extreme new physical system, the black hole. This was the paper in which we introduced the physics of this object, which, unlike all the preceding work, was based on the Kerr metric. And thanks to some very important idea of Roger and Penrose, who showed the possibility to, in principle, to extract the rotational energy from the black hole. We worked on this, defining as well the concept of ergosphere and the way that this process could occur. And it was precisely following this presentation that Christodoulou worked in the first step of finding for a Kerr black hole the mass formula. And this was for the case of the Kerr solution. The paper was received in 17 September 1970, followed by my paper on the with Dimitrius on the Kerr-Newman in March 1st, 1971. And March 11, just 10 days apart, there was the same result published by Stephen Hawking and followed by many, many other papers. What is the key point? Well, it was really after the attribution of the Crawford Award to Roy Kerr, we traveled from Sweden to Cambridge, and it was very, very nice to have the opportunity to go over. First, they told us that Stephen was very sick, that was not available. We were very sad with Roy. And while we were chatting in an office, a secretary came. He said, Professor Hawking would like to see you. Where? To the hospital? I said, no, you sit downstairs in his office. Boy, we ran down and we had a fantastic discussion for a few hours about the black hole physics. And then Stephen said, but can you give a seminar? And both of us, Roy and myself, gave a seminar the day after. And then after the seminar, what about tomorrow? Stephen said, well, you can come to dinner at my place. And this is this fantastic event which we had at his home with Roy, the wife of Roy, Stephen, and myself. It was a great joy, all this. And the main topic now being addressed is how to use in an astrophysical process an extractable energy in this mass formula, this mass energy formula by Christodoulou, Stephen, and myself. The goal is to explain the high energy emission in the MEV and the JEV, and there are currently important progress which we plan to continue next year in the MG16, where we will have, if necessary, an online version, or let's hope for the best. The first picture show Erbogorski, Giacconi, and myself in 1971. There, these were the two discoverers, Herb and Ricardo, of ScoX1, but also with Ricardo we work after the Uru to the identification of SenX3, a star accreting onto a main sequence star accreting on a neutron star. And this object, this family of objects, which we did not understand at the time, namely the evolution of this system, are precisely the one which gave, now we realize, which gave origin to the GRB, to the gamma ray burst. But what was the point we missed at the time is that when the second star, the main sequence star, gravitationally collapsed, the accretion of the material on the neutron star generated an enormous amount of energy, up to 10 to the 54. And then if you compute that energy, therefore the system with gravitational collapse of the companion becomes visible from the older universe. And therefore, instead of having one event in 10 to the 8 years in our galaxy, since we can see with 10 to the 54 the entire number of galaxies in our past light cone, the number of events is really observable, becomes once a day. And once a day, roughly, were the gamma ray burst discovered by the Villa satellite. In San Francisco, we had a meeting with Herb Gursky, which was then published in a very nice book, and Jan Strong presented there the first evidence. But the new era on GRB started in 1996, after 23 years, when finally Beppo Sachs gave evidence about the distance of this object, that they were indeed extragalactic, and up to there we did not know anything about their energetic, but indeed they were objects emitting 10 to the 54 ergs, and from the accretion of the binary star. The binary nature of GRB, I can just tell very quickly. The first successful proposal of relating GRB to an astrophysical cosmological source came from the vision of Zoltan Pashinsky and his school, and the two Chinese collaborators, Li and Mao Tzu, and of course other collaboration like Narayan, Piran, and Shemi, to propose that the short GRB were really originating from binary system of emerging neutron stars. When we turn from short GRB to long GRB, the general idea presented by Rees, Metzaros, Woosley is that the long GRB originated from from black holes. And the energy was released in an ultra-relativistic blast wave with Lorentz gamma factor up to 10 to the 3 given by Blanford-McKee. In our approach, which I will present now quickly, we assume that all the long GRBs, not only the short GRB, originated from binary system. These binary systems are composed of different combinations of CO star, neutron star, new neutron star. Only in some of these subclasses, the presence of a black hole occurs. And three subclasses are the BDHN, binary-driven hypernova, with the CO core and companion neutron star. And the difference of energetic is practically determined by the binary period. But in all this system, far from having a jet ultra-relativistic, all the emissions occur mildly relativistic in a specific, a different GRB episode. I show now a diagram about all the way we see all the possible short GRB and long GRB. This diagram is inspired up to the work of Cuvelier II in 1993, updated by Wang Yu. And here, the big difference between these two diagrams is that the right diagram is done in the rest frame of the source, and therefore one of the consequences that the difference between the short and long gamma ray bursts occur not as traditionally considered 2 seconds, but at 0.75 seconds. Again, and this diagram, which was presented in the paper by Wang Yu, we have the three classes of binary-driven hypernova, and we have the merging of short gamma ray burst. We will address now the binary-driven hypernova. What is a binary-driven hypernova? It's just the supernova explode in a binary. This is the case like SENX3, common envelope, then the companion neutron star explode, and here you have the explosion of the supernova accreting. When the supernova explodes, it creates, like in the crab, a new neutron star, and the supernova can the supernova accretes into the new neutron star and creates the afterglow. When the supernova accretes on the companion neutron star instead, it creates a vacuum polarization process and the JEV emission. Therefore, we have three different moments. The accretion of the supernova on the new neutron star, generating the afterglow, the accretion of the supernova on the companion neutron star, which creates a black hole, and the vacuum polarization process creating the JEV emission. But let's look at the novelty. The novelty of GRB 190114C was created mainly given by the Fermi gamma ray satellite, joint activity with the VLT, joint activity with the beautiful Neil Gehrels Swift Observatory, and again, this time in 190114C, joined also by the MAGIC Observatory in the TEV radiation, and also by the young satellite by the Chinese colleague Nanzhang, a collaborator, the hard X-ray modulation, which participate in this SgrA and this fantastic collaboration. But not only this space satellite worked on GRB 190114C, but up to 52 observatories on the ground. And the characteristic was, again, the fact that I go just to the three main results coming out of these systems. First, the afterglow. All the after and also the other, and compare them with the GRB 130427A, GRB 160625, and 160509. The characteristic of this afterglow, which originates from the accretion of the supernova into the companion neutron star, have a characteristic luminosity given by this formula with a fixed index, slowing down index, and is precisely from fitting the emission of the X-ray of this afterglow that we discovered that the explanation comes from synchrotron radiation at very mildly relativistic expansion speed with Lorentz gamma factor up to 2. And this, and then we could determine out of the slope and the energetic, infer the period of the new neutron star of the order of millisecond, which generate the energy of the afterglow. This has been presented in these papers, and let's go now to the outer branch, the branch which originates from the physics of the black hole. And here you have the JEV emission of GRB 190427, but with the JEV and also the TEV emission. And also in this case, if you take the BDHN, which generate JEV radiation, which out of the 380 BDHN which have been classified, all of them with an X-ray afterglow with the slope I showed before, only 25 BDHN are observed emitting JEV. And this is due to the particular geometry of BDHN, only the one seen from the top, normal to the equatorial plane of the binary, can emit JEV radiation. And again, from all of them have a luminosity which follows this particular power law, which is different from the one of the X-ray afterglow emission. But again, out of this, there was a fundamental progress last year, because we identified the inner engine of the GRB in the Papa-Petro-Wald solution, in which you have just a Kerr black hole not isolated, but evolving in time with a magnetic field along the rotation axis of the black hole. This theory was developed in great detail, and then from the fact that the black hole rotation energy is explain energetically the JEV energy, namely equating the JEV radiation in the power law and extractable energy of the black hole, we have determined the characteristic. We have determined the masses of the mass of the black hole. The first one being the one of GRB 190114c, in which the mass is 0.41 solar mass. Excuse me, the mass of the black hole is 4.45 solar mass, the irreducible mass 4.35, the magnetic field is 0, and the spin of the black hole is 0.4.
You have 5 minutes.
For the first time from the inner engine physics, we could obtain the mass of the black hole exactly in the range that we were expecting. And the black hole is not formed a priori, but is formed by accretion of the supernova into the companion neutron star, reaching the critical mass smoothly. And now let's go to the last point, which is by far the most, for me, the most exciting, the black holic quantum. From the theory of the inner engine, we have determined that the emission of the JEV emission and TEV emission does not occur continuously, but there is the emission of quanta, which relate the energy of the blobs of this quanta to the rotational energy of the black hole, and this is the formula. The energy of the quantum is given by h bar by omega effective and by the energy of the photon. This is in the paper of myself and Rueda. And what is very, very interesting is that this emission process occurs both in GRB and in active galactic nuclei. The only difference, the only difference in the process is the time scale, which scale with the mass. Therefore, in GRB 130427A, or in which is of the order of 2.4 solar masses to black hole, the characteristic time of the JEV emission of the quantum black holic energy emission is 10 minus 5 seconds. The energy, maximum energy, is of the order of 10 to the 18, which emit super also high energy cosmic ray, and the characteristic energy of each blob is 10 to the 36, and when you divide the 10 to the luminosity from 10 to the 36 to the just a moment, 10 to the 36, the luminosity is exactly the one of the JEV luminosity. When you go to active galactic nuclei, where the mass is of the order of 10 to the 10 solar masses, the characteristic repetition time is 0.49 day. Again, you can produce ultra-high energy cosmic ray. The energy is much big for the quantum black holic energy, and the luminosity is much higher of the order of 10 to the 43. Before closing, let me ask, can we see the black holic quantum? Well, we cannot see the black holic quantum yet in the GRB because the time scale is too short. But if we take the scaling law to an active galactic nuclei like M87, and these are the beautiful radio data of the Walker and collaborator from the Very Large Array in Socorro, then you can see as a function of day, let's go back to the previous, the characteristic time scale of the black holic energy in the case of M87 is of the order of day. And here you see, in terms of day, this emission of the blobs. And again, the reason we can see them is that they are in radio, and therefore we can probe they can probe very close to the origin of the black hole. The key point for our model is that the radiation from the black hole does not come far away at 10 to the 16 or 10 to the 17 centimeter expected in a fast wave relativistic, but comes directly from the black hole horizon. And a general conclusion there is we have 380 VDHN. They emit in the X-ray with the power law. We can infer the mass of the new neutron star. Out of 380, 25 VDHN are observed in the JEV. They again have a power law emission of the luminosity, and from that and the theory of the inner engine, we can determine the mass and the spin of the black hole. Well, this effort was shared by many collaborators, which I'm very, very thankful. especially if I have to mention that with Thibaut d'Amour, we first identified just a few days after the discovery of the GRB back in the 70s, a model based on a Newman black hole. Many of the ingredients and the energetic of 10 to the 54 was predicted, but the model was too early to be confronted with the data. Today we have the great advantage to have a very large amount of data, and therefore we can from this and develop step by step, day by day, a theory which can finally fit all the mass determination of the new neutron star, and for the first time, the mass of the black hole, creating smoothly in the accretion from the creation of a supernova into a companion binary neutron star. A long, long way, but we are very happy that 50 years after introducing the black hole, we have reached, thanks to the largest effort on the Earth on observational data, to reach this firm conclusion. And all this, of course, based on the fantastic theory of Albert Einstein, which has guided every single step. Today, even yesterday, there was a GRB. And we are currently studying, like every day, the mission of this fantastic system. There is still to understand what the GRB are for. What is their function? They are so unique, they are all over the universe. And we are starting to work on the idea that very likely the origin of DNA is due to the magnetized field and emission in synchrotron radiation from this newly born black holes. Well, to next year, 2021, where this result will be presented in MG16.
Thank you very much, Professor Ruffini. Thank you very much. We have a moment for question, and the question comes from Partha Sarati Majumdar. Can there be a gravitational wave burst like a GRB from a black hole? We cannot hear you. Can you just repeat? There is a problem. We cannot hear you a moment.
Yes. A very good question. What we have learned is that the formation of black holes in this 380 BDHN occurs very smoothly, following the supernova emission, the accretion on the companion neutron star, and then when the critical mass is reached, you have the formation of the black hole. Not at all like we expected. This is one of the greatest novelties. Not as we expected, the collapse at once, but smooth. And in these cases, although we measure very now of the order of 10 black hole masses, all of them over, of course, as expected, the critical mass, all of them with A over M smaller than 1, therefore, in the canonical theory of black holes, they do not emit a large amount of gravitational waves, because the transition, unlike in the short case where you can have two neutron star merging and gravitational wave emission, but in the long one, the process is much, much smoother. And of course, the most dramatic important point is that the energy which is coming out from the black hole, from the Kerr black hole, can be studied precisely because we violate the condition of having the Kerr black hole not stationary, non-stationary, evolving, and not in vacuum, but in presence of a magnetic field. That is essential in the world solution. And this is the only condition that allows this radiation to be emitted close to the horizon, almost very low Lorentz gamma factor, not larger than 2, therefore no blast wave, but very, very close to the horizon, and see the formation of the black hole in real time. I think we can definitely see this transition in all GRB, like if you see in our publication.
Thank you very much.
Thank you much.
Yes, we have to move to the program because we're a little bit late. So let's thank Professor Ruffini again. Now, next speaker is Professor Yuan. Let me see if we can switch. Professor Yuan, are you there? We cannot hear you, and we cannot see you either. Can you activate your microphone, please?
Yes, can you hear me?
Okay, we can hear you. And
Okay.
Your webcam?
Thanks.
Okay.
So let me get
Please
started.
proceed.
Yeah. Dear Remo, dear colleagues, good morning and good afternoon. It depends on your choice. This is Ye-Fei Yuan from USTC, University of Science and Technology of China. It's a great pleasure for me to give a talk in 4th ZLDovich meeting. I would like to thank Remo and Gregory for inviting me to attend this nice conference. Today, I will spend about 30 minutes to convince you that we can use Sagittarius star and M87 star, two nearby massive black holes to probe the strong gravity near the event horizon of black hole. Here's the outline of my talk. First, I will give a very brief introduction to the idea of strong gravity, the general relativity, from the point of view of analytic mechanics. That means I use language of Lagrangian, Hamiltonian, Euler Lagrangian equations to give you a general idea of geometricalization of gravity. Then I will focus on how can we study strong gravity near the horizon of black hole through the black hole shadow. As you know, the first EHT image, the event horizon telescope image of M87 star has been released. As a member of EHT collaboration, I will be very happy to share with you what can we learn from EHT image of M87 star, the central black hole in nearby galaxy M87. Finally, we'll discuss the future developments. Let's start from the Schwarzschild solution. As you know, Schwarzschild solution describes a spherical curved spacetime. Onto the symmetry, the spherical symmetry, means the spherical symmetry, there are only one metric function the GM over R here. So roughly speaking, the metric function could be considered as the gravitational potential, which is the original point of view of Isaac Newton. Now, let me spend several minutes to summarize the physics of strong gravity in order to get to the geodesic equation. How does the curved spacetime tell the test particle move? According to Einstein's suggestion, they can move along geodesic. So here we can have the action according to Einstein's suggestion. The resulting effective Lagrangian, that means Lagrangian gives us the same action. So the resulting effective Lagrangian has only the pure kinetic energy. Here, the kinetic energy means the square of the velocity, the four-dimensional, velocity in a curved spacetime. So we have a Lagrangian in our hand, then substitute this effective Lagrangian into the Euler-Lagrange equations. We can get the dynamic equations for test particles. Here is Lagrangian, effect Lagrangian you have seen in last slide. The key point is to solve the dynamic equations. That is to find the four integral constants. Actually, due to the symmetry, the spherical symmetry, it is very easy to find the four integral constants. Here is E, L, epsilon, and theta. It is very interesting to discuss the radial motion. In the following discussion, I will use effective potential to describe the radial motion of test particle in curved spacetime. This left figure shows the effective potential for massive test particles in Schwarzschild spacetime. As you know, from this effective potential, we can know the ISCO, the innermost stable orbit, the capture radius for massive particles, and the right figure shows potential, effective potential for massless particles, such as photon. This effective potential is very, very important for us to understand the black hole shadow. Actually, here we have two characteristic radii. The first is photo radius. As you know, this is radius of photo orbit. And also we have the impact parameters, also the capture radius for photons. It is about square 3 times larger than the photo radius. Actually, this cartoon shows the main physics of objects in curved space-time. Actually, the photon range is very, very important for the understanding of the size of the black hole shadow. For Schwarzschild black hole, the size of black hole shadow almost is photo range. This photo range is only depends on the mass. That means the black hole shadow is not sensitive, depends on the gas dynamics near the event horizon of black hole. It's almost only depends on the mass of such black hole. Above discussion is focusing on rotating black hole. As Remo mentioned, black hole can rotate very fast. So here I show the metric for rotating black hole, actually, there are only two free parameters in matrix of rotating black hole: the gravitational mass and the specific angular momentum A. So, as I said, roughly speaking, matrix is a kind of potential. So we have two potentials: the mass potential and also the spin potential. The spin potential is a function of m over r squares, m over r cubic. So that means spin effect. The spin potential is short range force. Also, the spin potential, the spin force, in some sense, is pure GR effect. Now let's go quickly to find the force integral constant of the test particle in QL space-time. From the symmetry, it is very easy to get the first three integral constant. That is because the stationary of the metric, and also because of the axis symmetry, we have E, and also L, and also the epsilon. The epsilon, in some sense, is energy. So the point here is to how to find the last integral constant, or as you know, eventually we get the cut constant from the Hamiltonian-Jacobi equations. That means solve the Hamiltonian-Jacobi equations, we give the first cut constant. Fortunately, we have found the all integral constant. So we have the generating function looks like this. So from this generating function, it is very easy to get the dynamic equations of test particles in QL space-time. So you just do some differential action. So that means here shows equation of motion in integral form. We can also get the equation of motion in differential form. If you are interested in the technical details, you can find all the derivations in Chandrasekhar's book, The Mathematical Theory of Black Hole. So, because gas moving near the event horizon of black hole is relativistic, that means they move very fast. So the beam effect is also very important. The Liouville theorem tells us the larger of the frequency of the photons, the larger their specific intensity. That means if the photon gravitationally redshift, they will become much dimmer due to the beaming effect. We can see this effect from the Liouville theorem. Of course, the opticals in curved spacetime will have other physical effects such as gravitational lensing, gravitational redshift, and also the effects of frame dragging if the black hole is rotating. So let's move to the second part. This figure shows a VOA image of our galaxy center. Actually, here is the Sagittarius A star, the central black hole in our galaxy. From the gas dynamics and also the stellar dynamics, we can measure the mass of Sagittarius A star, the result is the mass of the Sagittarius star is about 4 million solar mass. And also this figure showed the VOA and HST, VLBA observation of M87. You can see the jet here in the center, where they also have a massive black hole. The mass of the central black hole is about 6.5 billion solar mass. Actually, we can monitor S2 star to study the GR effects near the event horizon of Sagittarius A star. I think Stefan will tell us more. I think I should skip these slides. And also recently, Gravity, the VLTI, Gravity instrument, also captured several hot spots near the east of Sagittarius A star. Their orbital radius is about is almost near the east. So that means we can study the strong gravity effect from this hot spot. The key point, the main result, I think, is we can have some information about the dynamics and also the information of the magnetic field from the polarization of the properties of the hotspots. Here I show the black hole image. Actually, this figure is from the movie Interstellar. Very interesting. They are published this book, this figure in classical and quantum gravity. The first theoretical investigation of the black hole shadow can date back to 1979. In 2000, there's some work on the image of the black hole in our galaxies. The key point is, you know, the accretion flow near the Sagittarius star is ADAF. I will discuss later. Anyway, it's a kind of black hole accretion system with very low accretion rate. The typical, the temperature of iron and the electron are different. That means we have two temperature disk. The main radiation from this kind of accretion flow is the cyclotron radiation and Bremsstrahlung radiation. So why we choose Sagittarius star and the M87 is a target of Event Horizon Telescope. I think this figure show the reason. Well, in this table, we show the size of the black hole shadow. For M87 star, the angular size is about 18 microarcseconds. The angular size of our own galaxy, the Sagittarius A star, our own massive black hole is almost twice that of M87. For the stellar black hole, for example, the Cygnus X1, the angular size of the black hole shadow is very, very small. And also the main radiation is from X-ray. I think the X-ray, the resolution, angular resolution of X-ray telescope is only 1 second. We have a long way to have the X-ray image of stellar massive black hole like Cygnus X1. So this cartoon shows the accretion model, accretion modes with increase of the mass accretion rate. With the increase of the mass accretion rate, we have the EDAF. That means advection dominant accretion flow to the standard accretion model. That means the lower with if the accretion rate is very, very low, we have the EDAF mode. EDAF is also the inefficiently accretion flow. That means the radiation efficiency is very, very small. The gravitational energy is released, but it cannot be very efficiently released from the accretion flow. So the temperature of the gas is very, very high. It's almost near to its very real temperature. The typical temperature is 1 billion Kelvin. This figure shows a typical spectral energy distribution of Sagittarius A star. Here is at the radio band, and here is at the infrared and also X-ray. Anyway, we for EDAF mode, the radiation is very, very broad from radio to X-ray. And the key point is radiation is not thermal. That means we have very broad thermal radiation from Sagittarius A star. The peak is from the secretary radiation.
You have 5 minutes more.
Oh, really? Sorry. In 2009, we have a very detailed investigation of the image of Sagittarius A star at 1 millimeter. Actually, this is EHT observing wavelengths. So we'll give some predictions. So we are waiting for the image of Sagittarius A star. Actually, we already have the image of M87. The X-ray at the x-axis shows spin. From the left to right, the spin is increase. The y-axis shows inclination from bottom to top is from, that means from face on to edge on. But in most cases, we can see the black hole shadow. And also we can see the symmetry and asymmetry pattern of the radiation. So I think you already know the Event Horizon Telescope. The point is we should have a good resolution. The resolution should be near 25 microseconds. So this is UV coverage for the 2017 observation for M87. So basically, you can see the theoretical, resolution is 25 microseconds. I think you see this image for many, many times. So I think the key point is here we see the black hole shadow. The size of this shadow is roughly the photo realm I mentioned. we can do some GIMHD simulations to give some, that means we can have image library. From the image in this library, we can compare the theoretical calculations, theoretical image with observed image. That means we can get some informations about the properties of accretion flow. For example, the temperature of the iron, the electron temperature, and the number density, because actually the emission we have observed is from electron. Even iron have more temperature, where have very high temperature, and also the strength of the magnetic field, because the peak of the SED is from cyclotron radiation, and also the accretion rate. As you see, the accretion rate is very, very low. That means this is consistent. So from the size of the image, we can measure the mass of the black hole, because the larger of the size of the black hole shadow, the larger of the black hole mass. And also from the emission pattern, we have also have some information about the jet direction and the jet direction. This table summarizes the parameters M87 star. I think the key point is the mass we measured from the size of the black hole image is very consistent with the dynamical measurement. For example, from the mass we made from the stellar dynamics. Due to I ran out of time, so I have no time to discuss another recent work. Anyway, we can use black hole shadow to test the new physics. For example, test the equivalent principle. The key point is if we have a vector field which is coupled with test particle, they will change, basically in principle, they will change the size and the shape of the black hole shadow. I think I should go to the last slide. This cartoon shows the main result of this recent paper. That is different colors show the different observing wavelengths. That means if they are coupling between the vector field and the test particles, such as photons, it looks like a spectroscopy. That means the color it looks like a color rain. I think this is the last slide. The fridge developments. I'm eagerly waiting for the image of Sagittarius star, because in 2009 we give some predictions, and also the polarization results. I think the polarization image of M87 were published soon. So that's all for my talk. Thanks.
Thank you very much. Okay, we have time for a few short questions, and indeed there are questions already and even discussion in the chat. So I tell you, the first question comes from Supran Kazimpur Ishka. As Professor Ye-Fei mentioned, in the case of Kerr black hole, that Hamiltonian equation could be used to calculate the equations of motion in order to determine the orbits of test particle. My question is in this way how we can consider the effect of other objects on the orbit of test particle? Okay. Did you hear the question, or should I repeat?
I think the question means if we have other particles cannot be considered as test particle?
Apparently so. Yes.
Yeah, if so, I think the symmetry were broken. For me, maybe I can use post-Newtonian physics to investigate. In full general relativity, I think it's very difficult.
Thank you. Next question comes from Partha Sarati Majumdar. Why does the orbit of Sagittarius A not exhibit any perihelion precession?
Oh, because it's not test particle, it's gas dynamics. That means we have some gas near the event horizon telescope.
That's right. And Stefan Gillessen just commented that you should hear the next talk of his about this topic. Next question comes from Alexander Zakharov. When you presented shadow size of Sagittarius A and M87, practically you gave values of shadow radii. Is it correct?
I think this figure shows, yeah. This figure shows size with some confidence. I mean, basically, statistically, I think we get the right answer.
Okay, thank you. And there is one more question or comment from Manuel Hoffman about the rainbow image. This is also something one would expect from a modified dispersion relation for photons near the black hole. Maybe you could comment on this?
About the rainbow image. Yeah. Yeah. If we have some detailed information about the plasma near the event horizon telescope, maybe we can test the rainbow image. I mean, for best of all present calculation, EHT should go to short wavelengths to detect this rainbow image. The short answer is the present EHT cannot observe the rainbow image.
Okay, thank you very much. Okay, I think we should move to the next speaker. Let's send Yuan, Professor Yuan again. Thank you. Professor Gillessen, are you ready?
Yes, I'm fine.
Okay.
Okay, first of all, I would like to thank the organizers for having me give this talk on behalf of the Gravity collaboration. I would have very much loved to come to Minsk, but I think it's even greater that the organizers decided that we move on anyhow and have this conference despite the difficulties in the pandemic situation, because it's very important, I think, that life moves on and that we do the best we can instead of just stopping. So I'm very happy to give this talk. And as I said, I'm talking not on behalf of myself, but actually on behalf of the Gravity collaboration, which is a collaboration led by the Max Planck Institute for Extraterrestrial Physics, but then with very strong contributions from Paris, MPIA in Heidelberg, EPAC in Grenoble, the University of Cologne, institutes in Portugal, and of course ESO, who is our host for the telescopes. So here you see the whole team that has worked on the Gravity instrument, and the team actually has been mostly using, of course, this mountain parallel, and you can see that there's 4 telescopes, and that is will be, of course, the main point that we have 4 telescopes which allow to work together as an interferometer, thereby synthesizing a very large optical telescope. Our sweet spot is the near infrared. You can see here as a function of wavelength in the blue curve, the resolution you can hope to achieve. You can see that, of course, at radio wave bands, one gets a very high resolution, as we've just heard, under the name of EHT. In the regime of the optical, it's then the classical 1/diameter law. But there's a sweet regime where one actually can do interferometry, and this is marked by this excursion VLTI. And at higher energies, most of the astronomical observations get hard because you run into the extinction screen. And at higher energies, of course, the resolution will never be as good as it can be in the longer wave bands. And you can see that the near-infrared, the green band, which is the H and K band, is really a sweet spot. So we are left of the extinction. We have atmospheric windows there, and we can do interferometry. And this is why we have been concentrating on this band. And you can see here 2 full sky images of the Milky Way. On the top, it's the optical image. In the bottom, it's the infrared image. It makes it evident that the near-infrared is the better band to look through the Milky Way, because the extinction is only on the level of 3 magnitudes. And in the optical, we even don't know what the extinction towards the galactic center is, because it's so big we cannot measure it. 3 magnitudes is something which you can just compensate by a longer integration time. So that's why we use infrared observations. You can see here a color image obtained at the VLT from the Milky Way center. You can see it's extremely crowded. The box here is 4 light years, which is roughly the distance between the Sun and Proxima Centauri. So the stellar density in the solar neighborhood is, maybe we would see 10 stars in this image. Whereas if you look here, it's 100,000s of stars, and it would be obvious that astronomy would be a major topic at any school you visit, because the sky of a planet around such a star here would, of course, be tremendously full of stars. If you try to zoom in into the center, you can see that the images sharp as you would hope they are. And the reason is that we hit the atmosphere. So you need some technical tricks to be better than that. And the standard trick nowadays is adaptive optics. You can see here how adaptive optics manages to resolve out all the stars. This is obtained at NACO. It's a 3-color composite. So you take 3 different wave bands and then assign it to different colors, and this gives a very natural looking image, because we are essentially also looking at thermal emission. So that's very similar to what we're used to from the solar radiation. So that's a very nice image. And the center here, you can see that if you look at the center for 16 years, you can see actually that stars are moving. In particular, there's one object which we call S2, which is going around in a 16-year orbit. So this is, of course, very exciting if you have a Keplerian ellipse. And currently, we have to say it's not only one ellipse which is there, but so this is the red one here. This is by far the best star, but we have 40 orbits. S2 is the best because it's the shortest period. It happens also to be the brightest. And we recently had a pericenter passage of the star, which happened on May 19 in 2018. It's clear that this deserves dedicated observations, I think. So from this, we know that there's a mass. We can also locate the mass because the infrared offers also a few stars which are both infrared sources and radio sources. And these radio sources then give us the link to SgrA star, which is the radio source. And this in turn, of course, can be put in relation to Bracon quasars. So you're actually in an absolute reference frame. This is work by Marguerite et al. So we can actually locate the mass. And you can see here that the position of the mass we derive from the orbit, and the position of radio SgrA star, they agree to much better than 1 milliarc. And here you can see a plot from the year 2015, where you can see that the position of the reconstructed mass actually is at the position of SgrA star. And this essentially brings us to a conclusion why we are sure that SgrA star is a black hole. You've seen that there must be a big mass. We can calculate it from the Keplerian orbits. It's 4 million times the mass of the Sun. The error on this number is below 1%. From VLBA data, we also know that the radio source such a star must be more heavy than 1 million solar masses, simply because it's not being shaken by any other objects around, so it falls through like a stone. So it's a much more heavy object than what one sees actually around it. Work by Margrit and Andreas Brunthaler. If one takes infrared and VLA radio data together, you can see it like I've just shown, that actually the mass and such a star coincide. So that's what you have just seen. And now what is missing is a size estimate. So how do we know the size of such a star? And there's a few things you can do. You can look at the timescales of the variability, from which you conclude the time that the object needs to be on the level of a tenth of an AU. More recently, in a precursor of the EHT, the radio size has been determined at 1 millimeter to 0.4 astronomical units. And with gravity, as I will show in a minute, we can actually see that the mass needs to be enclosed within 0.5 astronomical units. So all these things together, you have to cramp 4 million solar masses within 0.5 AU. That's quite extreme. And you can even go further. You can think of an object which has a surface, but then you would expect that actually there's an accretion flow onto that surface. The surface would heat up, and we would see that surface as a thermal emitter, but we don't. And thereby, Avery Broderick and Avi Loeb have concluded in 2009 already that the object cannot have a surface. So I think taken together, it's pretty convincing evidence that this is a black hole, and I think it's actually the best black hole we know of in terms of how sure we are that this is a black hole. So the main limiting factor during the observation is source confusion. You can see here, if you have no adaptive optics, you're limited to the dashed circle, which is lambda over R naught, the size of the atmospheric turbulence cells, which is roughly like 40 centimeters. It's equivalent to saying that the best image you get is as good as you would get it from a 40 centimeter telescope. Hence, it's a big achievement to have adaptive optics, because then we can exploit the 8 to 10 meter class telescopes, and we get at the level of 50 milliarc second resolution. We didn't stop there, but we actually went on and do interferometry. So we use the distance between the telescopes, which is another factor 10 or 15 larger. And the resolution is then lambda over 2b. And that gives us then a milliarc second regime. So this resolution is, of course, what brings us closer to the black hole. And this is what we have realized in the last 10 years or so. Here you again see Parnell Mountain with the 4 telescopes, how the light can be combined. The light travels underground to a common laboratory. And one way to think of this mountain is, this is a very big mirror, and it works just as a simple single mirror. Unfortunately, this mirror, however, is painted black in many, many places, and only 4 little holes are open. But from this picture, you can see that you still would expect an image which has the resolution of the large mirror. It just will be of very poor quality. And this is exactly what happens. Interferometry delivers high resolution, however, with a very complicated point spread function. The images are not straightforward to interpret, but you rather have to model them. A very big difference to the Event Horizon Telescope in the optical regime is that you need to do the fringes online. So you cannot record the individual waves, but you actually have to create your fringes as you observe, and then you record the fringes. For the EHT, it works differently. Each telescope records the waves, and then you only need the atomic clock data to actually synchronize these, and you can then form all the fringes later in the laboratory because you have the actual wave recorded. Much different here. Nevertheless, the sizes of the objects are mostly encoded in this fringe amplitudes. So you can see here, if the size gets bigger, the contrast goes down, and opposite. And the position of the phase encodes the position on sky. So this is the way we can derive images. In the end, it's only Fourier transform. So it's the so-called van Sittard-Zerniger theorem, which relates the object distribution on sky with the interferometric variables. And here's the instrument which we have built. You can see it's a cryogenic vessel, a lot of electronics, a lot of cables going in and out. But in principle, it combines the light of the 4 telescopes to create 6 baselines. And here is one example how that looks like. You can see here an interferogram where actually S2 and SGA star both have been in the beam. You can see as a function of a baseline length, you can see, for example, the fringe contrast. And the points are the data, and the model which we have is these lines which you can see. And we actually, you can see this model fitting includes source parameters. So, for example, the separation vector, the brightness ratio, the colors of the sources, but also instrument-related parameters like a bandwidth smearing or injection per telescope. If you do that correctly, you can come up with such a model and thereby measure, for example, the brightness or the separation of the two sources. And you can see, of course, that the high frequency of this oscillation, this is what gives in the end the high precision of the data. If you do that a few times per night, you can actually do more. You can actually reconstruct an image, and you can see here probably of the world's sharpest near-infrared image. It's at 3 milliarc-second resolution. You can see SGA star and S2. The elongation of the sources is this point spread function, which is given by the telescope geometry. And the separation vector here is only 22 milliarc-second, but extremely well resolved, of course. So the interferometer is here at full power. Maybe it's interesting to compare how good the UV coverage is, because we have 4 telescopes only. So that means we have 6 baselines, but we actually have the full K-band, and the K-band is from 2 to 2.4 microns. So this is a 20% width, and that relates then to the width of these bands, which you can see in the plot here. You can see that each of these UV tracks actually is a band, and that helps, of course, a lot in the UV coverage, and thereby I would think it's more or less comparable to what the EHT gets, where you get per telescope only one single track. So imaging with 3 milliarc-second resolution and astrometry at the 10 microarc-second level, just to illustrate, if the S2 orbit, if we take that on sky, it's more or less as big in size as a stadium on the moon would be. So that's more or less the size what we have observed. 3 milliarc-second resolution then means that we are able to detect a car in that stadium, and the astrometry which we can do, so the precision by which we can locate object is 10 microarc-seconds, corresponding to just a coin on the moon. In other words, if they play a soccer game in this stadium, we can do the video assistance, whether the ball was in the goal or not in the goal, we can do that from Earth. That's the level of resolution, of astrometric resolution we get with gravity. And you can imagine, we are on sky since 2017. We have a very big number of results. We can measure extremely precisely the galactic center distance and mass. We detected the redshift of the star S2. We tested the equivalence principle in that system. We have seen flares around the black hole. We have detected the Schwarzschild precession. So all this is on the galactic center, but the flux distribution of such a star. But even beyond the galactic center, there's fantastic things with gravity. For example, it excels really in obtaining spectra of exoplanets, simply because it delivers the highest contrast between the planet and the host star because of the high resolution. Or we have, for example, spatial resolved the rotation of a broadline region of the quasar 3C273, which also is then a sub-parsec scale. Of course, I will not talk about this. I will stick to those topics here. It's long enough an agenda and interesting enough. So here you can see the orbit of S2. It's this showcase star. We have started in 1992. This is this data point up here with the spectral imaging at a 3.5 meter telescope, and the positional errors were on the level of 2 milliarc-seconds. The star then rushed through pericenter in 2002, except that people did not know at the time. And then from 2003 on, you can see here that the adaptive optics really gave extremely tiny error bars. And we have then the interferometry data since 2017, and you can see how extremely well we have also followed the pericenter pressures in 2018, 2019, and note that we have a 2020 data point up here, which was actually just 3 days before the lockdown in Germany. We were able to get this point, so we were there on the mountain and flew back essentially on the last minute to still have this data point. And you can see here how the images look like, which we obtained. These are true images reconstructed. you can see SGA star as a variable source, and you can see how the star S2 is actually moving around the black hole during the months indicated as written here. And we've actually seen the star move day by day here in April. You can see that each observing night which we had, we have seen the star advance a little bit here. You can see in May, it moved on at quite high speed. Pericenter was the 19th of May. The star reached 8,000 kilometers per second, so mildly relativistic. And then in June, we were able to observe again. May 19 actually was a new moon period, and that's where the observatory goes to the optical astronomers, not to the infrared astronomers. This is why we don't have a data point there. Also, we have sampled extremely well the radial velocity swing. You can see here the radial velocity curve from the year 2000 to 2020. Each of these points requires at least a 3-hour integration. And you can see that in 2018, we have been sampling extremely well with an error which is not visible on this plot because it's 12 kilometers per second only. Note the units. The star goes up to 4,000 kilometers per second and then swings down to minus 2,000 kilometers per second. And together with the proper motion, that is then the 8,000 kilometer per second 3D speed. And the first thing you can do is you can actually compare the motion on sky with the radial velocity, and the only parameter which is between those is actually the distance. And so it's a very direct measurement of the distance. And you can see the distance to the galactic center here is 824 plus minus 9 statistically and 45 systematic parsec. You can see how well this orbit fit actually constrains the distance to the galactic center. So you can see here, we also even know that the measurement error of the radial velocities determines our statistical error, and the calibration error of the astrometry determines our systematic error. If you put this into context, here you can see how small the gravity error ellipses are compared to what was measured before. You can see that it's a tiny, tiny yellow ellipse compared to all the data which you might have seen in talks before. Another way to show the improvement here is, for example, how well can we measure the orbital period. When we detected the orbit in 2002, the error on the period was 7 months. Remind, the period is 16 years. After a few years, it was at 3 months. Then in 2009, we were 3 to 4 weeks. In 2017, we actually had it down to 5 days. And now it's down to 10 hours. So that's how well we have improved. And the last step, of course, is the interferometric improvement. And due to the high speed, we actually expect that 2 relativistic effects set in, and namely this is the transverse Doppler effect and also the gravitational redshift from SGA star. Both should affect the emission of the light from S2. And this is exactly what we have seen. You can see here the residual against the Keplerian part of the orbit, and you can nicely see how the 2018 data shows this peak reaching 200 kilometers per second, of which 100 kilometers per second are due to the Doppler effect, and 100 kilometers per second are truly the redshift of the S2 photons in the gravitational field of SGA star. Or you can zoom in a bit more. You can see how well they've measured this peak and also how it came down again. Or if you express it in a parameter, you can see that we have measured here at 1.045 plus minus 0.043. So very well determined that the parameter is 1 and not 0, where 0 would be a Keplerian behavior and 1 is the relativistic behavior. Actually, I wonder why is this only 23 sigma? The reason is that actually we have to do a 14 parameter fit here, and the Kepler orbital elements allow sufficient degree of freedom that they eat up a lot of the effect. And this was noted already in 2006 by Shai Zucker and Tal Alexander, where in a paper in 2006 they wrote, in this context, there are 2 possibilities to break the degeneracy. One is to use astrometric data, and this is exactly what we have done. It's the gravity astrometry which has broken the degeneracy such that the spectroscopy actually shows the redshift term as expected. But we have not only measured the velocity, but we have actually measured the velocity both from the hydrogen atoms and from the helium atoms. So we are actually using 2 different clocks. And that, of course, sounds immediately like the equivalence principle. And we can compare the 2 velocities. And you can see in the bottom plot that there's no deviation from 0, which is consistent with saying that both clocks actually experience the same redshift. And so we can set a limit on the beta parameter. It's not particularly good compared to many other measurements which have been done. However, it's a very different regime of gravitational field strength. You can see that we are by far the ones who go out most to the right. So the laboratories on Earth, of course, have a very weak delta phi only, and the annual modulation due to Earth orbit is also rather small. And so we are in the dynamic, with a dynamic measurement here at a high delta phi over c square. Also, you would expect that the
5 minutes left.
Okay. Also, we expect that the orbit should precess, the famous effect of Mercury, which you see here transiting in front of the sun. And here's an artist impression of how precession should look like. Actually, if you do the calculation, the orbit is mostly not changing its angle. So mostly you have just a flat line, and then actually you see that at pericenter you get a change in the orbit orientation, and then it's more or less flat. So it's not a constant process, but it's actually more like ticking of a clock. And another way to look at this is here shown here. So this is how it should look like for S2. You can see the star, as it approaches the black hole, is following its orbit, and then at the orbit, the two solutions, the Kepler and the Einstein orbit, then start to deviate, and you can see that one needs then to wait a little bit that the difference builds up. And how big or how small actually the change in the orbit trace is here in this plot, you have to zoom in a little bit to see that. You can see it here. Here you can see actually that the orbit is not closing, but this is the size of the effect. And nevertheless, we have detected this with more than 5 sigma significance. You can see on the right side here, the angle of the orbit, it's essentially coming in at one value, then it's doing this swing by, it jumps a bit back and forth, and then settles on a new value. So the orbit has rotated. It's mostly in right ascension, so in the x coordinate, so to say, and you can see compared to the Kepler orbit how the GR orbit is slowly going down, deviating here. But by 2020, our data point, which we obtained this year, the difference is not even 0.5 milliarc seconds yet. Yet the interferometer is good enough to actually determine this change. And here, let me just show you what you get if you give these data to a graphics department. So they model a nice star on this orbit, and then it gets scary as we approach the monster of the black hole. We fly by, and then actually the orbit is changed a bit, and you can see that we are then on a different orbital trace. If you would want to detect the spin, we actually know that this will be extremely hard with S2, simply because the spin effects fall off like R to -3. So we would need stars at closer radii. And at that point, astrometry gets harder. However, spectroscopy gets easier. And we think that this is actually a case for using the extremely large telescope, which ESO is currently building, where we have 20 times the collecting area and hopefully can reach much fainter objects. In particular, we should be able to reach down to G dwarfs, which are solar type stars and which have very rich spectra, and from which one can determine velocities with much higher precision than one can do from these hot young stars we are currently observing. Let me come to Sagittarius itself. It's a very underluminous source. It's only a fraction of the Eddington luminosity. And you have seen a similar plot already. And notice here this 200 solar luminosities is here. So the black hole is not shining even at 200 solar luminosities. So it's very dim. And the explanation why it's dim is actually has been a topic of many, many researchers. You can see a lot of names down here. And it's actually a complicated combination of a low accretion rate, of low efficiency in the angular momentum transport, of low efficiency in the energy transfer, and actually most of the gas needs to be ejected back out, so it's not actually making it to the black hole. But beyond that, we see that Sagittarius is flaring in the infrared. You can see here from the adaptive optics data, a little movie, and you also can see that from time to time there is flares occurring. And it turns out that with gravity, we are of course doing much better on this, because we just resolve out these things. And you can see that we essentially at all times see SGA star, and we can detect much fainter flares also. So these measurements are, of course, much better at high resolution as well. And that means that we can, for example, look at the flux distribution here. Look at the left plot first, which is the AO data set, which essentially reaches its limit at more or less 3 millijansky, and look at the right plot where we can go all the way down to 0.1 millijansky. And that means that we, for the first time, actually see a turnover in the flux distribution. So we have a typical near-infrared flux for SGA star here. And the conclusion remains the same, that above 5 millijansky or so, we actually see something which is different. So this is not the standard behavior. There's an excess here beyond the log normal distribution. And this is what we call the flares. And we think that the typical near-infrared flux might originate from a non-thermal component. So you can see here that this non-thermal component actually is visible both in the very long radio bands and in the near-infrared. And the flares are synchrotron emission of transiently heated electrons. So you take a few of those electrons, you heat them up, and then you get infrared emission and X-ray emission. And this is exactly what we see in these light curves, that both infrared and X-ray flare up at the same time. The speculation is this might be an analog to solar flares. So it's just a bit of different geometry, but in principle, you have some picture like this, as SGA Yuan was proposing in 2009. And the flares actually should orbit roughly at 10 microarc second radius, or a factor larger than that. And you can see here a simulation from Roderick and Loeb in the year 2005. And this is what we have based our science proposal for gravity on. So you can see here how these flares actually should move around the black hole. This is 2005 and 2006. In 2018, here we have the observation. You can see how the flare motion actually has moved around. In this case, it's actually a clockwise motion. And we have 3 of those beautiful flares where we can see the clockwise motion. So we actually see gas surrounding the black hole at very few gravitational radii. So what we see is a hotspot which goes around the black hole. And this comes on top of the normal variable emission, which is these blue colors here in this movie. And you can see the hotspot, which is going around the black hole in addition. And this is sort of a thunderstorm or a flare, like a solar flare. And also a very basic conclusion I would like to mention here is that it means that the mass is indeed confined to within 0.5 astronomical units or 2 microparsecs. And this, I think, is in a very strong contrast to the model which has been proposed by Becerra-Vergara recently, where 56 kV dark matter fermion was proposed to explain the black hole. And you can see that our flare data simply don't match there. You would need a much higher fermion mass. And then I think, of course, one can describe the S2 orbit with the model, but the G2 data, this gaseous source, you cannot describe anymore in this model. So I think this should change the conclusion of that paper from very basic principles. Also, we have the signature in polarimetry, not only astrometry, but also the polarization changes of the black hole. And if you take all this together, you can actually determine the inclination of the system, and you can also see the typical radius. I'm finished in 2 slides. You can also see that the radius is 8 RG here. So we can actually determine both the parameters from the combined data. We have 3 flares here. You can see them. If you go at them and come up with some figure like this, you can estimate what is the orientation of the rotation. And it actually matches the orientation of a lot of stars, which we know of massive stars. And thereby we think that actually the orientation of the system we see is reflecting the angular momentum of the gas inflow from these very hot and luminous stars in the vicinity of SGA star. So we don't see the spin of the black hole. We rather see the initial conditions of the gas, how it flows in. That's concluded by Jean Ressler, working together with Elliot Quartert in Berkeley. Okay, here's my summary. I think SgrA is the laboratory for general relativity around black holes. We know the distance, the mass extremely well. Also look at the error bar on the angular size. We know extremely well how big the object would be. We measure GR effects in the percent regime. The redshift of S2 is detected at more than 20 sigma. We tested the Einstein equivalence principle. The center precession has shown up. And we know the system so well due to many researchers' work. And in particular, in opposite to M87, we have access to dynamics because we see motion stars, flares, and in that sense, we have a clue of a key towards the temporal aspect of the metric around the black hole. And with that, I would like to conclude and thank you all for listening.
Thank you, Stefan. Thank you very much. It's a nice talk. We have several questions to you. The first one comes from Patra Majumdar, and the question is, how would one observe gravitational lensing from S2?
Of course, all of the stars are lensed, but in order to have an efficient lensing configuration, the star should, of course, be aligned behind SgrA star, which is not. So S2 is never lensed. And the second point about this lensing equation is that the most efficient lens is if the lens is halfway between the observer and the object. So the best lensing SgrA star provides is actually 8 kiloparsecs on the other side of the Milky Way. And that means the stars close to the black hole, if they get lensed, they would be extremely faint. I think they are 23rd or 24th magnitude. So it's a tiny effect. I think the astrometric effect...
Thank you very much. Thank you.
I think the astrometric effect of that would rather be visible than the actual second image.
Thank you very much.
Thank you. Next question from Li Jing Shao. Is an S-star always in thermal mechanical equilibrium along its orbit? If not, does the oscillation in structure and so on dissipate the orbital energy?
I think it's true that the stars get, let's say, tidally heated a bit. However, these stars are still very compact objects. So this object S2 is roughly, when it comes close, it is I think 1,500 Schwarzschild radii. So this is still far away from the black hole. So the effect of the tidal forces are still rather small. It would be different for giant stars. So if you have a giant star, that would noticeably be deformed, and then of course you convert orbital energy to internal heat.
Thank you. And last question from Alexander Zakharov. What do you think about opportunities and perspectives to constrain alternative theories of gravity with S2 observational data?
In general, I think we don't know enough about the astrophysical background. So we would need to know how many black holes, how many neutron stars, how many white dwarfs are actually sitting there beyond the big black hole. All of these objects would actually have a gravitational effect on the orbits of all the stars, and that might actually be much stronger than all the differences one can do. Of course, we have played the game. I think we give also some limit on the Yukawa type of potential you can play the game, but this always assumes that one has a pure system, that you have only S2 as a perfect test particle around the black hole. And I think nature is more dirty. We expect that there's actually a sea of additional masses which make these measurements simply, I would think, almost impossible, because you would need to first know all of those hidden masses.
Okay, Professor Gillessen, thank you very much again. Thank you for joining us, and we have to move to the next speaker. Okay. Next speaker is Professor Amati. He will speak about the THESEUS mission. Professor Amati, are you there? We can
Hello,
hear you.
good morning.
Yes.
Do you hear me, Gregory?
Yes, we can hear you.
Okay, so I guess you can hear, can you see my screen now?
Yes, perfect. Yes.
Okay, so thank you very much and good morning to everybody. And thank you also to the previous speakers for the excellent talks. In this talk, I will provide you with a short summary of the science case and concept of the THESEUS space mission. So THESEUS stands for Transient Energy Sky and Earth Universe Surveyor, of which I am the principal investigator on behalf of a very large international collaboration. And you can find much more details on the THESEUS website and on these two white papers that together with many other papers you can find on the archive. These are the two main references up to now for this mission. This mission is aiming at fully exploiting gamma ray burst for cosmology and multi-messenger astrophysics, and of course will also provide unique clues to the physics and nature and progenitors of gamma ray burst. So addressing some of the main open issues that have been put forward also in the previous talks. THESEUS is a mission under study by the European Space Agency within the Cosmic Vision program, is presented and developed by a large international consortium, full European consortium coordinated by Italy. So we acknowledge fully support by the Italian Space Agency and the Italian National Institute for Astrophysics, and together with UK, France, Germany, and Switzerland having major roles in the mission, and with relevant contribution also by Spain, Belgium, Czech Republic, Denmark, and Poland, and many other countries. So I go to the main scientific objectives of the mission. As anticipated, we aim at fully exploiting and eventually exploiting the high potentiality of long gamma ray burst for cosmology, in particular for investigating the early universe. So we're talking about investigating the first billion year of the universe, the epoch of cosmic reionization, formation of first stars and first galaxies. At the same time of fully exploiting the short gamma ray burst for multi-messenger astrophysics. So as you can see on the sketch on the right, the short gamma ray burst is the most prominent electromagnetic counterpart expected from neutron star, or neutron star black hole mergers, producing also gravitational waves, as has been beautifully demonstrated by the simultaneous detection of a gravitational wave signal from such a source by LIGO in 2017, and simultaneous detection of a short gamma ray burst. But more in general, the THESEUS missions aims at providing a substantial advance on the whole transient energy sky, so capable of detecting and characterizing many classes of transients in the sky, and of course providing a fundamental service and synergy with the large, very large observation facilities of the future, like ELT, SgrA, CTA, Athena, in all the electromagnetic domain, but as well as in the gravitational wave and neutrino, so the so-called multi-messenger domain. So first of all, let's talk about exploiting long gamma ray burst for cosmology. As we know, long gamma ray bursts are the brightest phenomenon, electromagnetic phenomenon in the universe. They can release, as in isotropic equivalent radiated energy, more than 10 to 54 erg in a few tens or a few minutes, tens of seconds or a few minutes. So they can be detected up to the very early universe. And actually, as can be seen in this plot on the top right of the slide, a few of them have been detected actually up to a few 100 million years after the Big Bang, which means a redshift of 8, 9, or even more. Long gamma ray bursts, there is mounting evidence on the progenitors. Remo also discussed the scenarios for the progenitors of long gamma ray burst. But the main key is that this huge luminosity and detectability up to the very universe is associated also to the fact that they mark star-forming regions in star-forming galaxies. So by simply accumulating a statistical sample of very Vereshchagin gamma ray bursts, we can reconstruct the star formation rate evolution in the first billion year of the universe, which is of course a key observable for understanding the star formation evolution, but also for understanding the cosmic reionization, which is thought to be mostly supported by the ultraviolet photons of the first population of stars. At the same time, long gamma ray bursts, some of them, a small fraction of them, may also be produced by population 3 stars. So this means providing a direct detection of population 3 stars. To give you an idea of how impressive is the capability of gamma ray burst of tracing and characterizing the universe, you can have a look here on the bottom left. This is the image, near-infrared image of the afterglow, so the fastly decaying, mostly power decaying emission following the burst in the X and gamma rays. So a fading source detected at a redshift 9.2. So this is a direct image of the consequence of an explosion of a star or a binary neutron star system in a few hundred years, so 300-400 million years after the Big Bang. So it is true that at this redshift now we have some very large, massive galaxy, very redshift galaxy detected through, for instance, the Hubble Frontier Fields program. But these are only the tip of the iceberg. These are the brightest galaxies detected mostly through gravitational lensing. This is instead through gamma ray burst, a direct detection of an object exploding so close to the, in terms of hundreds of billion or million years to the Big Bang. So as I mentioned, and as it can be shown in the sketch on the right, the star formation rate evolution, which again is a fundamental measurement for understanding cosmic ionization and the formation and evolution of first stars and galaxy, is subject to a very large uncertainty at redshift higher than 6 or 7, and this will be true to larger redshift even in the future. So accumulating a statistical sample of very redshift gamma ray bursts, simply counting the number of gamma ray bursts as a function of redshift, if instead of 4 or 5 high redshift gamma ray bursts as we have now, we have 50 or 100, we can of course solve this large uncertainty on the star formation rate evolution, in combination of course with next measurement by JWST, ELT, or even SgrA. At the same time, one of these objects can also be a direct measurement or direct detection of a population 3 star. But even more impressive is the capability of very redshift gamma ray burst of providing us the detection, identification, and localization of very redshift galaxies that are actually invisible even to the large facilities in the optical or near infrared. These are the 6 images of taken with the Hubble Space Telescope in the direction of 6 very high redshift gamma ray bursts after the afterglow, so this fading source faded completely away. As you can see, there is nothing. So we know that in this direction, at this redshift, there are 6 very redshift galaxies, only because we were capable of detecting and localizing accurately the gamma ray burst in the X gamma rays and following them with very quickly and with a very sensitive telescope. This clearly is telling us that gamma ray bursts have a unique capability to detect and localize very redshift galaxy, the first population of galaxy, the bulk of weak, low mass, low luminosity galaxies that is below the threshold of even the large facilities in the optical and infrared. And moreover, if we have a look at this spectrum, this is the absorption spectrum, an example of an absorption spectrum obtained against this, again, this kind of fading counterparts of gamma ray burst. So of these galaxies that are invisible to the largest telescopes, not only we know that they exist, where they are, at what redshift they are, how many there are, but also we can characterize through absorption spectroscopy on the afterglow of the gamma ray burst before it fades away, the metallicity, as we can see on the right, the neutral hydrogen fraction, for instance, through the Lyman alpha feature, and also through, again, these features due to the absorption in the intergalactic medium, the properties and the evolution of the properties of the intergalactic medium around this very primordial galaxy. So these are really impressive capabilities. They are very well known by experts of the early universe. The big issue here is that despite the huge efforts in the last at least 20 years, by space, many space and ground facilities, we are still stuck to a very few gamma ray bursts at Vereshchagin 6. And this is due because of the huge observational inefficiency introduced by the fact that you need to combine space telescopes with ground telescopes and so on. So the main aim of THESEUS is to fill this gap and provide in a few years of scientific operation from 50 to 100 gamma ray bursts at redshift higher than 6. On the other hand, as I mentioned at the beginning, the other phase, let's see, of the science case of THESEUS is its capability of detecting, localizing, and possibly measuring the redshift of most, all, or many of the high energy transits in the sky. So especially short gamma ray burst or soft X-ray emission, and first of all, those that are associated to sources of gravitational waves or neutrinos, or as demonstrated even recently, very high energy photons like those detected by MAGIC in the GV or TV domain. This means that THESEUS will provide a fundamental contribution also to multi-messenger astrophysics. To give you an idea, this is the beautiful picture, observational picture that we got in 2017. So it was already put forward since several years that neutron-star merge. So the merger of binary neutron-star system or neutron-star black hole system could produce gravitational waves, could produce a short gamma ray burst, and should also produce through the very neutron-rich material around it emitted after the merger and the radioactive decay, the formation of very heavy elements, an infrared emission that is so-called kilonova. And this was all confirmed in August 2017, when there was the detection of a gravitational wave signal from a neutron-star system, a detection of a short gamma ray burst by the Fermi gamma ray burst monitor in a direction consistent with the one from the GV signal, and just after a fraction of a second. And then, thanks to the efforts of many telescopes on the ground and in space, the detection of the so-called kilonova emission in the near infrared. All this effort took many hours or days, many facilities, and THESEUS, at least for a fraction of these events in the future, aims at doing all of this by itself, detecting and localizing the short gamma ray burst very accurately. I mean down to a few arc minutes or even to a few arc seconds. So to compare to the location capability of the Fermi GBM, which is at least several square degrees, and detect and localize possibly the kilonova emission. So all by itself. So really a huge step forward in the observational efficiency for this kind of science. How will this be possible? So such a mission like THESEUS is actually in the mind of the worldwide scientific community, so gamma ray burst, high energy transients, multi-messenger astrophysics community. So this kind of mission, which as we propose for THESEUS, joins monitoring capabilities, very extended monitoring capabilities, gamma ray burst monitor capabilities, very much extended in terms of field of view and energy band. So if you think of the Swift Burst Wireless Telescope, the BAT, as a very narrow energy band, 15 keV, 150 keV, too narrow for allowing a full characterization of the spectral properties, to allow the detection and localization of very soft X-ray flashes, X-ray events, and so on. And especially if we want to substantially improve our capabilities of detecting and localizing very redshift gamma ray bursts that are, of course, most detectable in the soft X-ray regime because the radiation is redshifted, of course. We need a unique combination of a huge sensitivity in the soft X-rays that we provide through the so-called soft X-ray imager, that are these cameras here that are based on the so-called lobster eye telescope technique using microchannel plate optics. In a few words, they allow to focus soft X-ray on a huge field of view of the order of the steradian, which means thousands of square degrees. When we think of a normal X-ray telescope, we think of a field of view of alpha degree, 1 degree is very large. Here we're talking about thousands of square degrees. We join it with another monitor, gamma ray imaging spectrometry, which is, by the way, the main contribution by Italy, in addition to the overall leadership of the mission, which provides the detection and measurement of the prompt emission of gamma ray bursts from 2 keV up to 10-20 MeV, which exceeds by far the capabilities of any past and present gamma ray burst detector. And then the mission concept foresees that for each gamma ray burst that is detected and localized by the monitor or transit of interest, the spacecraft, as is for SWIFT, slews very quickly and in a few minutes in order to point a near-infrared telescope, a 70-centimeter class near-infrared telescope, to the direction of the source to catch the fading afterglow. And as I showed before, allowing to detect and localize down to a few seconds the direction of the gamma ray burst, the host galaxy, to do eventually the redshift. So in this way, THESEUS, as is shown in this plot, which shows the spectral peak energy versus the peak flux, which means spectral hardness as a function of brightness of the gamma ray burst. This combination of instrumentation and mission profile will allow THESEUS to detect and localize any kind of gamma ray burst. In particular, as you can see on the bottom left region of the plot, the bulk of the population of Vereshchagin gamma ray burst that is still beyond the capabilities of current detectors. For instance, here we show in red the Fermi GBM. All this population is currently missed by current instrumentation, and instead THESEUS will have the right capabilities to unveil this population, but at the same time it will maintain and keep the capability of detecting and localizing short gamma ray bursts, which are key for multi-message astrophysics, ultra-long gamma ray bursts, which may be signature of population 3 stars, X-ray flashes, subenergetic gamma ray bursts. So people who work on gamma ray burst and the related gamma ray science related to gamma ray burst know how is important to progress on all these classes and subclasses of gamma ray burst. That, by the way, Remo already anticipated in his very nice and beautiful talk at the beginning. So these plots show in a more quantitative way the comparison between the capabilities, the capabilities of THESEUS with respect to previous or current facilities. This is a luminosity redshift plot. You see in yellow where stand the current gamma ray burst detected by current facilities, and you see in violet instead what will be the population detected by THESEUS. So THESEUS will be capable to go to much lower luminosities and to much higher redshift. And this on the right compares the current rate of gamma ray burst with measured redshift coming from the combination of SWIFT, Fermi GBM, CONUS WIN, so I'm mentioning the main gamma ray burst satellites, combined to robotic telescope on the ground, large facilities on the ground. And instead in red and then better in green, you see the capabilities of THESEUS, the detection rate per year as a function of redshift, that could be obtained by THESEUS alone, by itself. So it's really a huge improvement with respect to SWIFT. So just in a few words, if with the combination of SWIFT, Fermi GBM, CONUS WIN, all these telescopes on the ground in the last 20 years, we managed, or 15, let's say, we managed to gain, to identify 6 gamma ray bursts, more or less, at redshift than 6. THESEUS by itself, in 3 years, so we are comparing 6 gamma ray bursts in 15 years, in 3 years, THESEUS will be capable of detecting 40 or 50 of them, and in a few years of mission, 100. And of course, for the early universe science, this will allow THESEUS, for instance, as we can see on the top, an example, on the top left, these yellow points with this small uncertainty to put very important constraint on the sub-formation rate evolution. At the same time, as you will see on the right, thanks to the follow-up, for instance, by ELT, to measure the metallicity of a kind of redshift 8 or even 9 host galaxy, as we can see on the bottom left, to put important constraints on the parameters for cosmic ionization. So the escape fraction, so the ultraviolet, the density of ultraviolet photons produced by first population of stars as a function of the escape fraction from the host galaxy. These are parameters needed to actually assess if the first population of stars can be the main source of cosmic ionization, and so on.
Mr. Amati, 5 minutes.
Sorry?
You have 5 minutes.
Okay, so I just try to conclude again, showing the capabilities instead for multi-messenger astrophysics. I remind again this picture in which it is shown how THESEUS, through the detection and localization of short gamma ray burst, possible detection, as you can see on the bottom left here, of soft X-ray emission expected by some models after the neutron star mergers, if the remnant is not a black hole but a supramassive fast speeding neutron star, and the emission, the so-called, as I mentioned before, kilonov emission coming from the radioactive decay of very heavy elements forming in the neutron-rich material expurged during after the merger. To give an example of the application, so if with THESEUS we are capable of identifying and localizing the electromagnetic counterpart of several tens of gravitational wave sources, in the era, we are talking about a mission for next decade, when we will have advanced LIGO, advanced Virgo, CAGRA, and other facilities, and hopefully the Einstein telescope or cosmic explorer, so the so-called third generation of gravitational wave telescope. For instance, by putting together information from the gravitational wave signal and the electromagnetic signal, we can, of course, do, for instance, not only the physics of these sources, but a lot of cosmology, measuring with a very high accuracy the Hubble constant or the other cosmological parameters, because, of course, you have a model-independent, also cosmological independent measurement of the distance by modeling the gravitational wave signal, and you have the measurement of the redshift, thanks to the electromagnetic domain. By combining both, of course, you can have a very powerful tool for measuring cosmological parameters. As I mentioned before, in addition to cosmology, multiversal astrophysics, THESEUS will provide a huge step forward in the understanding of gamma ray burst and many other classes of sources, but here I focus on gamma ray burst, as I already mentioned, especially thanks to its very large energy band from the soft X-rays to the soft gamma rays. It can unveil the bulk of the population of soft gamma ray burst, X-ray flashes, under luminous gamma ray burst. It can provide the measurement of the spectrum of the prompt emission from 0.3 keV up to 20 MeV. Here I show only a portion of this huge energy band spectrum, which covers will cover more than 5 orders of magnitude. So colleagues like those, again, in the group of Remo and so on, which are always analyzing gamma ray burst data from Conus Wind, from GBM, knows how important is the measurement of the spectrum over this huge energy band, which will allow to discriminate, as shown here, between different models for the prompt emission for the physics of gamma ray burst. That is still a very important open issue, which is still beyond the possibility of current detectors, which are sensitive only above 10 keV. Here I show that below 10 keV, you can discriminate these models that are instead not distinguishable with current measurements. We can also exploit in the very high sensitivity in the soft X-ray, detect this kind of absorption features, which were very few, 1 or 2 of them detected also by the BeppoSAX satellite at the end of the 90s, which was the only to carry very sensitive X-ray detector for gamma ray burst for the prompt emission, through which we can identify redshifted absorption edges. For instance, here we identify a neutral iron K edge redshifted by estimating a redshift of 0.85, which was later confirmed by the spectroscopy of the Ops galaxy in the optical, which means that we can also use X-ray measurements to measure the redshift of gamma ray burst with a machine like THESEUS. And more in general, if we manage to, we will get hundreds of gamma ray bursts with measured redshift and very well measured spectrum, the spectral peak energy, which is key, again, a key observable for the physics of gamma ray burst, but also for its possible use through correlations with the luminosity, the radiated energy of gamma ray burst, for measuring, for standardizing them, somewhat standardizing them in a way similar to type 1a supernovae, and measure cosmological parameters. I mention again here the big synergy of THESEUS for early universe cosmology with future large facilities like ELT, with Athena. All these facilities need a transient machine like THESEUS to fully accomplish their scientific case that include gamma ray burst, but they need a gamma ray burst or transient machine like THESEUS to know where to point, at which redshift is a gamma ray burst, where is the gamma ray burst, of course. The same for multi-messenger astrophysics, I already mentioned. Straightforward synergy with gravitational wave detectors, neutrino detectors of the future, and again, all the large electromagnetic facilities. I mentioned also that THESEUS foresees also general observatory science. So this instrument can also be used for a guest observer science for many other science topics. For instance, the infrared telescope of THESEUS can also be used to study exoplanets, just to give a completely different science case, to give the idea of this instrumentation that can perform also more general different science cases. So I already mentioned about the consortium. I'm just conclude with the timeline. So THESEUS is under study by ESA in the framework of Cosmic Vision program as a 5th medium-sized mission to be launched in 2032. So we are currently in the concluding phase of the so-called phase A study, the first part of the development of the study, together with other two missions, SPIC and Envision. Envision is an orbiter around Venus. SPIC is a large infrared, mid-infrared telescope. In June 2021, there will be the final selection of one of these three missions. So this is simply a summary where I want to remark that the THESEUS mission concept, if at the end selected on next year, will allow to fully exploit the leadership and the heritage of European community, also of course in collaboration with all worldwide collaboration, especially Europe, the science, the technology, and again allow to fully exploit the scientific capabilities of the large facilities of the future in the electromagnetic domain, multi-messenger domain, in which a lot of efforts, money, and science work is being invested by Europe and worldwide communities. So I thank you very much, and I invite you to have a look at our website to register as a contributing scientist and to help us in shaping as best as possible the science case of THESEUS, so to maximize our possibilities of being selected. Thank you very much. I concluded.
Thank you, Professor Amati. Thank you very much for this wonderful talk and interesting tips for gamma ray burst science. We have a question from Professor Ruffini. What is the time resolution of THESEUS versus Fermi gamma GBM for prompt emission? Can you hear me?
So, Gregory?
Yes, yes.
I cannot hear the question, sorry.
Should I repeat? Okay. What is the time resolution of the THESEUS with respect to Fermi GBM?
Yeah, so Remo, thank you for the question. The time resolution in the main GRB detector is a couple of is a few microseconds. With a much larger effective area with respect to the GBM. So on all aspects of the study of the prompt emission, from the spectrum to the timing domain, our instrument will be much better than the GBM. You have to take into account that the GBM is a very small set of detectors. So it is really it is true that it goes up to, in principle, several tens of MeV, but very, very low efficiency. And this is why many of the spectra of the GBM can be fit also with a cutoff power, which is clearly due to the the low efficiency of these detectors above 500 or 600 keV, unless for very bright gamma ray bursts. So as I remark, the GRB detectors on board the THESEUS will cover an overall energy band from below 1 keV to 10-20 MeV, where with a more or less 1,000 square centimeter effective area from a few keV up to at least 10 MeV, and a timing resolution of a few microseconds. So I look forward, Remo and all of the colleagues interested in collaborating with you for simulation. We have on the website already there are available scientific tools for simulation, response matrix, background files, and you can go there. We can collaborate and really perform very nice simulations.
Thank you very much, Lorenzo. Once again, we have to move to the next last speaker of this session, which is Professor Lämmerzahl. Can you hear us? Yes. Okay. Thank you very much. Yes. Please proceed.
Seconds, and we are ready. So thank you very much for giving the opportunity to talk here. I will talk about testing general relativity, and in doing so, I will first describe the test which leads to general relativity, then tests which look for the consequences of general relativity. But I also will go a bit more detail to recent tests of the occurrence principle with the satellite microscope and the recent test of the gravitational redshift, improved gravitational redshift with the Galileo satellite, and then we come to an end. So by describing tests of general relativity, one may take a scheme which has been designed by Ehlers, Pirani, and Schild in a constructed axiomatic approach to general relativity, and this is also somehow included in the approach by Clifford Will in his book. And this starts with the uniqueness of light propagation. There are only one light ray in one direction. And this means that at every point we have a unique light cone. This has been tested very well with a precision from 10 to minus 15 to 10 to minus 30. For example, the independency of the velocity applied from the source, the isotropy, Kennedy-Thorndike time dilation, and so on. So the next point is that there's the universality of free fall or the weak equivalence principle. There's a coordinate system that for each point we may have a coordinate system so that all bodies fall according to the inertial law here. And this has been shown on Earth at best by the torsion balance experiments in the group of Adelberger. And the best result was that the equivalence principle is valid to the order 10 to minus 13. Now with the microscope, we are approaching now 10 to minus 15. We have seen 10 to minus 14. With all data, we will see 10 to minus 15. There are also some experiments with particles with a spin, with charged particles, and we are looking forward to test the equivalence principle for antiparticles. Then we have, of course, to test the compatibility between these two structures. So the geometry which is given by the free fall and the geometry which is given by light. So the compatibility then states that no particles move faster than light. This also can be tested in the lab with 10 to minus 6 precision, and with physical tests, this goes up to a 10 to minus 21. And then finally, one has to make a statement about clocks, or if one understands how clocks are built off, about the uniqueness of quantum mechanics, and this is called local position invariance. This means if you have two different clocks which are showing the same time, maybe they have the same ticking rate, but the ratio is constant, then they move along two different ways and then come together. Then the time is different. This is the twin paradox, which we also have in general relativity and special relativity. But in principle, it also may happen that the ticking rate is different, and this last point forbids the ticking rate to be different. And this is the universality of the gravitational redshift, or the uniqueness of the clocks. This has been tested with a precision up to 5 times 10 to minus 7. And this all together makes up the Einstein equivalence principle, and the consequence of this is that the gravity is described by a curved Riemannian space-time. And from that, so if you have this Riemannian matrix, then you have to think about how this matrix now to be described. And this then is given by an Einstein field equation. There is no
no approach operationally to come to this these equations. You can make a parameterized post-Newtonian approach, and then we can discuss how deviations from the Einstein equations are excluded by the experiment. But there are some loopholes. For example, there are no all-Finslerian effect included in this parameterized post-Newtonian approach. This is a bit historical. So what also has to be tested is that gravity in the non-relativistic regime will be as given by the Newton potential. This implies a special law for the gravitational potential, and also describes, so to say, the non-relativistic limit of the Einstein equation. This can be described, for example, deviations from a Newton can be described, for example, by a Yukawa potential with the strength and the range. And there are important experiments for small ranges because they are sensitive to predictions which come from string theory, and also for long ranges which are very precise, very much excluding any strength due to satellite experiments. One also may think about to look for an isotopic part in the Newton potential. And this also has been tested with atom interferometry and lunar laser ranging, restricting these anisotopical coefficients to be smaller than 10 to minus 5 or 10 to minus 9. Another issue is the Aktio gleich Reaktio, that gravity, so to say, is symmetric, and this can be described by a formalism designed by a Bondi. So you have an inertial mass, a passive gravitational mass, and an active gravitational mass. The active gravitational mass creates the gravitational field, the passive reacts on the gravitational field, and the inertial mass we know. So this is the two-body system here, and for each body we have 3 different masses. What can be shown is that if the ratio of the active and passive gravitational masses for two bodies is different, that is, such a coefficient is different, then we have a self-acceleration of the center of mass of this system. And this describes the violation of axial equal reaction for gravity. And the vanishing of C12 means that masses of the same weight create the same gravitational field, independent of their composition. And this also is a kind of equivalence principle, that the statement is independent of the actual composition of the body. This has been tested, for example, by Kreuzer in the group of Robert Dickey. So he took two bodies of different composition, but of the same weight. And if you assume that they create a different gravitational fields, and you have a torsion balance here, then this may be attracted a bit more than this. So by interchanging these masses, this torsion balance should start to swing. And this has not been observed, and this leads to an estimate of the C to the order 10 to minus 5. One may also go to lunar laser ranging. The moon has a certain structure. We have a geometric center, but we also have a center of mass, which comes that the iron core is a bit displaced from the silicium core, from the silicium mantle. And this then, since these are two different materials, this should lead to a self-acceleration along the line of between these two centers. And if you calculate this here, then this means that the velocity of the moon should accelerate. This means that the distance between the moon and the Earth should increase, and this can be discussed, can be observed very precisely with lunar laser ranging, leading to this estimate and this new laser ranging data with a new project and with improved data from the interior of the moon. This also has the potential to be improved by 2 or 3 orders of magnitude. If we now have approach to general relativity, then we can define what are our measurements or our measurement apparatuses. So we may define what is a standard clock, what is a clock, yeah. And this you have here an observer and the particle passing this observers and this light going back and forth between the observer and the particle. You can describe the radar distance between these two bodies. With this radar distance, you can define the spatial velocity, and from that you can define the relative spatial acceleration between the two bodies. And the statement now is that if a freely falling observer observes for all freely falling particles, always neglecting relative acceleration, then the observer is equipped with a special clock, with a special parameter, and this clock now is called the standard clock. So this is an operational procedure. And with this standard clock, you also can define a standard distance, yeah? Because you have a clock with the velocity of light, which is defined. Then we have a well-defined unique distance based on the velocity of light and clocks. Also, we can define what rotation is. This is based on the Perihelion bouncing photon. You have a central satellite and the auxiliary satellites, and you send the light ray from the central satellite to the auxiliary, and this will be reflected back in such a way that it passes against the central satellite, and the other satellite has to be adjusted in such a way that this passing light ray hits the satellite, and so this goes further and further. This defines a spatial vector here, and also a transport of the spatial vector. And this spatial vector is Fermi transported. This then defines operationally in this way what rotation is, or what is not rotation, and everything what is moving against it. This is given by rotation. So now we know what a clock is, we know what a distance is, we know what rotation is. This is given by the theory itself. And just a side remark, it can be shown that the atomic clocks are standard clocks. This has been, so to say, shown already by Parker and Pimentel in 1982. They described the hydrogen atom in curved space-time within just standard general relativity, and they have shown that the energy levels will be distorted through the space-time curvature by this here, the curvature tensor times the Bohr radius squared. Of course, this is the natural scale here, and this if the curvature is such large that this plays a role, then the atomic clock is of course not a standard clock, not a good clock. This may be happening at the rim of astrophysical black holes, but on Earth this term leads to an effect of the order 10 to minus 42. Nowadays, the clocks have a position of 10 to minus 18, so this is far beyond any experimental reach. Now, if you now have general relativity, this is then given by the Einstein equation, by the geodesic equation, which we already discussed here in this session. If you have extended objects, you have to go to a very complicated Matheson-Papapeto-Dixon equations. And we have timekeeping given by the proper time here given through this operational approach. And with these elements, we can now describe all the experiments which are now there. So, which are testing the consequences of general relativity. This is the deviation of light, gravitational lensing, the shadow of black holes. So this is all the effects on the light rays. Then we have orbital effects. This is the Perihelion shift, the Lense-Thirring effect, which is now very well understudied with the Lagos and Lares satellites by Cipollini. A third satellite will be launched also this year. So at the moment, they are approaching the percent level of accuracy, going towards the sub-percent level in the next years. Then we of course have the back reactions, the nonlinear effects of a general relativity given by the High-Staler quasar, first indicating the existence of gravitational waves. Also, the influence of the space-time geometry on extended bodies has been shown by the Schiff, that is the Schiff effect. This has been shown by the Gravity Probe B mission, which has been launched in 2004, and they succeeded to show this Schiff effect, the effect of the space-time curvature on the precession of a gyroscope to the order of 0.2 precision. Then we have the effect on clocks, gravitational redshift, started with Pound Repka, then the satellite, the rocket experiment GPA, and I will talk about Galileo. And then we have the Cassini experiment testing the gravitational time delay. And then we have an effect which has not yet been seen is the gravitomagnetic clock effect. This is the clock effect in analogy to the Lense-Thirring effect. And then, of course, we have gravitational waves. All these effects confirm general relativity to a precision of 10⁻⁴ to 10⁻⁵ in terms of the ppn parameters. Now we will go to two particular experiments, microscope and the Galileo. A microscope is a space mission where you measure the occurrence principle through the observation of two test masses in space. In space, you have a periodic situation, you have infinite long free fall, and you have the full gravitational field of the Earth. Or there are three important arguments in favor to go to space. We are partner of this project, and our part here was to test these accelerometers in our drop tower and to do the modeling of the performance. The main part of the measurement devices are cylinders made of different masses, which are equipped with electrodes, and by means of these electrodes, one can now orientate the two cylinders and observe the motion of cylinders, the hypothetical violation of the equivalence principle, which would then lead to a relative acceleration between the two masses here. This is these are the two test masses in the housing, and here it is how these housings are located in the satellite. The test masses, so we have two pairs of test masses. One pair is the science, so the science unit equivalence principle pair of test masses made of platinum and titanium, and then we have a reference science unit which consists of two test masses made just of platinum, so we can see whether there are systems, so we can compare or eliminate systematic errors from real errors. And here the main thing is that it is possible to rotate the satellite. So if you just have the situation as depicted here, any deviation from the equivalence principle would lead to a signal which has an orbital period. And this then is, of course, the same period. Most of the errors or the systematic errors will also show up. In order to decouple these two types of errors, one can rotate the satellite so that the frequency of the science signal then has a different value than the orbital frequency. And here you see the full satellite here, and this is the main instrument again with the two test masses, and you see it is rather complicated. These are the two test masses. These they have to be manufactured very precisely within micrometer precision in the total, and this has been manufactured by the German Physikalisch-Technische Bundesanstalt in Braunschweig. A major issue was the charging of the test masses. So for that we have a gold wire between the two test masses and the housing. And this gold wire has a diameter of 7 micrometer. And this was a very critical part and very complicated to handle with. And this also was the reason that the mission has had a delay of 2 to 3 years. But at the end, everything worked very well. So finally, we had the launch, and this is the so to say the basic equation here for measuring the force. So as I told, we have 2 capacitors here, and the test masses are moving inside here. And so by the modulation of the test mass, according to the modulation of the position, one can measure very precise the force between the 2 cylinders, and this is related to the gradient of the actual capacity these capacitors have, and this is, so to say, the way to measure the signal. Here you see the noise and the decoupling of the 2 frequencies, and here the going down of the noise in these 2 accelerometers. So after a certain number of orbits, the noise goes down with 1 over square root of n, of course. And finally, there was the first result in December 2017. Where 1 order of magnitude improvement compared to the best ground test has been reported. So this is 2 times 10 to minus 14. And now we are, but for this first analysis, only 9% of the data has been used. And now we are using all the data, and we hope to approach the 10 to minus 15 level. The second,
5 minutes. 5 minutes.
Okay, yeah. So I'm now going to the gravitational redshift. So the first test was by Pound and Repka in the Stanford with a precision of 1%. Then we have had the GPP maser, GPA maser in 1978. So they just tested these coefficient alpha here. So it's a deviation from the pure inference of the Newtonian potential, and the Wesson-Levine result was that alpha is a bit better than 10 to minus 4 for the alpha. This was just one parabolic flight of 10,000 kilometer height. Now in 2014, the first real operating Galileo satellites 5 and 6 have been launched with a Russian rocket, Soyuz rocket with a frigate upper stage. But there was a malfunction, and after the launch, both satellites had an eccentricity of 0.233. So green is the target orbit. Red was the orbit after launch, and this would mean that every day or 2 times a day, because they complete one orbit 2 times a day, they have a height difference of 11,600 kilometers. So I immediately called the space agency to use this for the space experiments, and in fact they agreed to that finally. But they had to move up a bit the lower part of the orbit, because they hit the Van Allen belt. So at the end, they had an eccentricity of 0.16, and a height difference of 8,730 kilometers 2 times a day. So this is almost 10,000 kilometers. So in practice, we have
2 times a day we have a GPA experiment. Of course, it is not as easy, so Einstein would be very happy for that opportunity, but it's not so easy because the clocks are not as good as in the GPA experiment. So we have a passive hydrogen maser here with the uncertainty of 10 to minus 14, and a rubidium clock with a precision of a bit worse than 10 to minus 14. And yeah, you can calculate the gravitational redshift, and to calculate how the time accumulates here. So we are always testing the alpha here, and we also completed this here with a quadrupole moment of the Earth. The measurement was the measurement data was the pseudo ranges, which were all the influences on the time of the signal between the satellite of the Earth, and this is very cumbersome. But finally we succeeded, and all the clocks also worked not very well. You see, red is no working clock, orange is badly working clock, and the green are good working clock. So it was not so very good. But we at the end we could choose a good clock and made the conclusion. But on the first side, the blue dots are the measurement points, and the red curve is calculated without any fit, and so this coincides very well. But if you look at the detail, then you see fluctuating part here, and the question was how to interpret these fluctuations. So we had here, this was in the numerics. We performed a last square fit model, also a Bayesian approach, including the quadrupole moment of the Earth, and also with the parameters, the clock residuals and the clock offset and drift parameters. And at the end, so we have we had four clock sessions, and these are the 4 clock sessions in one plot here, so to say. And you see that these clocks are not so good. So finally, we could take this clock after long discussions, and using these clocks, then we could see how the precision or the Van Allen variance went down, so that we could really approach the interesting level of 10 to minus 5. And then we discussed the temperature, magnetic effects, also so to say, we also included the effects of the solar radiation and other effects on the satellites, and also discussed whether there are some effects of the ground clocks. For that, we had some modeling of the satellite. Also had an extra campaign with the ESA, with the laser ranging to the Galileo satellites in order to confirm our modeling. And with that, we could obtain so to say something which is 1.5 10 to minus 5, and we could estimate the temperature, because there were data on Earth which estimated the influence of temperature changes on the performance of the clocks. There were no temperature measurements on the satellite. Unfortunately, we also calculated the influence of the magnetic field on the orbit. Also could have using this measurement on Earth, and taking everything together, we then ended up at 1.5 plus minus 1.6 10 to minus 5. This then gave an improvement of the until now best measurements of GPA by a factor of 5. So at the moment, the gravitational redshift has now a confirmation of the order 10 to minus 5.
this is not such a big improvement, but it was an improvement by a chance. And the one message is if one could take a dedicated clock mission, there are certainly the potential to have at least 2 orders of magnitude more improvement. So, okay, all these open questions which are also influencing clocks, for example, the influence between quantum mechanics and the general relativity, and also the question of what is then I'll get to the end of the take-home messages. Until now, there's no single test contradicting to special and general relativity. What is not yet measured as a prediction of general relativity is the gravitomagnetic clock effect. This is if you have a rotating mass, then the clocks orbiting this mass in a counter orientation then show up here a different clock, a different time. And this is the gravitomagnetic clock effect. What also should be done is to explore the gravito and quantum range by taking more quantum systems to perform tests of general relativity, for example, clocks. And of course, what is a big unknown is what is dark matter, whether this is a particle or a modified gravity. This is not clear. So thank you very much for your attention.
Thank you, Professor Lämmerzahl, for this wonderful talk. Thank you. We have a question from very active participant today, Partha Sarati Majumdar. What is best accuracy of the measurement of G? Newton's constant.
Of G, this is all of the order 10 to minus 4, or this is there's a pendulum experiment of the group of Fowler I've forgotten which are also earlier made some experiment, and they have a measurement of the order 10 to minus 5, as I remember correctly. This is one measurement which also coincides with the co-data recommendation. There are new measurements using atom interferometry. This has been carried through by the group of Guglielmo Tino in the Firenze, and but I think they are at the order 10 to minus 4, so 1 order of magnitude less. But of course, quantum experiments have a lot of potential because they are their plan is to use cold atoms in space, and then you have more time to accumulate small forces, and then perhaps the accuracy may go up by several degrees of freedom.
Okay, thank you. There is a comment from Professor Ruffini. Very impressive talk with a lot of progress. Let us be ready for many invited reports at Marcel Grossman 16 meeting next year.
Yeah.
Right. And there is another question from Andrew Beckwith. Could the properties of dark matter, if experimentally confirmed, help the resolution of general relativity lack of fit with GR? So I guess there is some quantum mechanics probably. Could it lead to resolution between the two theories? Probably there is a misprint. General relativity and quantum mechanics, I guess.
This might be, yes. This is not excluded. So it might be that is, but this is pure speculation. Some kind of vacuum fluctuations also, which is triggered also by the strength of Gurch or the gravitational field. But this is pure speculation. So the question is whether this is a particle or whether this is not a particle, whether it is a real substance or whether this is due to a modification of gravity. And if it's a modification of gravity, then it might be that it is something which has to be done with
with quantum mechanics. If it's just another particle, then I think it's not very probable that it is contributing to the question whether to the question of the compatibility of quantum mechanics and the classical general relativity.
Thank you very much, Professor Lämmerzahl, and let's thank all the speakers of this session. Thank you.
Okay.